Hello and welcome to this episode of Physical Attraction. It is the latest in our nuclear fusion odyssey, and we're going to be trying to answer the question, can a startup build a star? So arguably the stories of humanity's attempts to build a sun on Earth started in earnest with the ambitious dream and promises that weren't kept. The cynics would tell you that this is where the story ends. Now great strides have been made as we've seen in the two main approaches to fusion, magnetic confinement fusion and inertial confinement fusion with lasers, but problems have still remained. As generation after generation of fusion device merely revealed more subtle and complex ways for plasma to be disobedient, the initial optimism has died away. And as scientists search for ways to smooth out each successive instability, optimistic predictions about the timeline on which fusion power will be available have become clichés and then bitter jokes. One of them is, for example, fusion is the energy source of the future, and always will be. Devices got larger and more complicated. Spitzer's first stellarator was built in a disused chicken coop and fit on a tabletop. The facility that houses the Wendelstein 7X, Germany's state-of-the-art stellarator, cost €1 billion. The experiment itself took 18 years to construct and was a decade overdue. And the story in inertial confinement fusion was similar. The largest ever experimental laser fusion experiment, the National Ignition Facility, saw its budget quadruple from initial estimates to end up being over $3.5 billion. When it became clear that it would not achieve ignition or scientific break-even, the facility has shifted and focused to weapons research. Today, for many people, humanity's efforts towards nuclear fusion are synonymous with the construction of the ITER tokamak, by far the largest fusion experiment ever carried out. An international collaboration between the EU, Russia, Japan, China, India, South Korea and the US, the ITER tokamak will cost over $20 billion to construct. And while the aim is to achieve Q equals 10, a 500 megawatt power output for 50 megawatts of energy input to the plasma, equivalent to many conventional power stations, a further device demo is going to need to be constructed to function as a practical power plant. Now, on paper, given how hard that fusion has proved to achieve, not for want of trying, it may seem as if only a huge international collaboration on the scale of ITER has a prayer of success. Just as it took the Large Hadron Collider, multi-billion dollars and multi-countries collaborating together to find the Higgs boson, there is a sense that science is moving into an era where it takes more than a few gifted experimentalists with sealing wax and string, as they used to say about the Cavendish Laboratory in Oxford, to change the world. Only science and engineering on a truly industrial, maybe even a global scale, with virtually bottomless budgets and thousands of collaborators, can hope to succeed on a project this fiendishly complicated. But of course, with that international collaborative spirit comes significant disadvantages. We've already described how ITER is hardly the most dynamic and swift-moving of organisations. In fact, it's decades behind schedule, and there have been many problems that have been caused by the issues of just trying to keep this collaboration going across so many different nations. And for all of these reasons, not everyone is on board with the ITER timetable. In the shadow of ITER, there are countless smaller fusion projects. Some are startups focused on a particular novel means of fusion, others are spun out from research efforts at big technology companies or from plasma physics laboratories in universities. They're often funded by backers who can afford to risk millions chasing the prize of fusion. We're talking about Jeff Bezos, Elon Musk, Bill Gates, Paul Allen of Microsoft, Peter Thiel. These are just some of the people who have backed private fusion projects. There's even a venture capital fund, Strong Atomics, which is solely devoted to investing in fusion startups. Now, if fusion lives up to the hype that it's been given and becomes an integral part of the energy mix, replacing fossil fuels, it's clear why ambitious startups would want to be the first to achieve net power output and reap all of those financial rewards. But there are deeper concerns about putting all of humanity's fusion eggs in the ITER basket. A classic parable is that of the primitive civilization that decides to go to the moon. Their top scientists build successively bigger balloons, and note that each one can reach a greater height than before. Naturally, they spend decades constructing colossal balloons, convinced that the next one will finally achieve their goal. It's true that tokamaks have the most impressive record. They've been studied for decades and we're getting better at understanding how their plasmas behave. They hold records for confinement time and energy production. The improved stability of tokamaks led Western scientists in the 1960s to abandon the stellarators and the pinch devices they'd worked on, as soon as they confirmed that the Soviet prototypes were performing as well as intended. But there will always be those who think that those other ideas were abandoned too hastily. And there is always a risk that, as we venture into new territories for plasma behaviour, some new instability might emerge that means that ITER can't achieve its targets, in the same way as NIF was unable to achieve break-even for inertial confinement fusion. One example might be, for example, if the disruption problems are difficult and you can't really mitigate them, these disruptions, these violent explosions of plasma that occasionally occur when you run the machine towards its upper limit of availability. If disruptions are a real issue in ITER and a few disruptions would end up destroying the machine, then you're not going to get the results that you want out of that particular reactor. And if that's the case, who on earth would be willing to spend billions of dollars on the next fusion reactor then? We can build these machines until the cows come home. I'm wondering in my own mind, how long do you have to beat a dead horse over the head to know that he's dead? And that is, of course, the quote from Senator John Pastor on the Appropriations Committee about magnetic confinement fusion back in 1964. It's 2019, so people who have his way of thinking are probably thinking that even more now. There is then perhaps the more troubling question. What if ITER performs exactly as it's supposed to? Then, by 2027, scientists would have proved that, with a couple of decades and billions of dollars worth of funding, you can produce a relatively small amount of power in an extremely complicated way. The first actual attempt to harness that energy in a power plant, demo, can't begin serious construction until the data from ITER has been analysed. Even an extreme optimist would conclude that, if ITER's roadmap is the only route to fusion, it won't power anything until 2050, perhaps much, much later. And when you consider that these things are taking, 5-10 years at the minimum to build, the idea that you could deploy them in time to replace our fossil fuel infrastructure on the timescale that we need to is just ludicrous. I mean, people will talk about fusion as a possible breakthrough solution to climate change. Maybe in the 1980s it was, but now it just won't arrive in time, and we know that. So I think on this timescale, arguing that fusion will save us from danger at climate change seems like a fantasy, because if we haven't replaced all of those fossil fuel infrastructures or done something else by then we're going to be in serious trouble. So if that was part of your rationale for backing fusion, then you obviously have to find some way of doing it faster than the ITER timescale. Indeed, those behind the startups would argue that if ITER is truly the way to nuclear fusion, as its Latin name suggests, then fusion is at a commercial dead end. Private investors who are willing to risk billions of dollars on a power plant that uses experimental technology are few and far between. Investment is easier to come by for smaller projects that hope to realise a profit more quickly. Now, we've talked about how the venture capitalists are investing in these startups, but you have to remember that there's two different types of investment for these people. There's the type of investment where you're going to try and generate a profit in relatively short term, a banker investment, so to speak. And then there's venture capitalism, where you effectively throw money at, say, 10 different ideas, and you hope that one of them will be the next Facebook or the next Google, the next company to not just sort of slowly, steadily double in value and give you back money, but instead increase in value by hundreds of thousands of times and then make you a billionaire off the back of one of those successes. So when venture capitalists are investing in things, quite often they're expecting a lot of that money to go down the drain for unsuccessful projects, in the hope that, as it's a high-risk enterprise, some of the high risk will be rewarded. Now, this reluctance on the part of actual investors to invest in building nuclear power plants, because building a nuclear power plant is not like a venture capital regime, okay? If you're building a power plant, what you're doing is looking to realise a profit by selling the electricity on a relatively small timescale. So this reluctance is really a big part of the decline of nuclear fission power, from 18% of the world's electricity share in 1996 to just 11% today, as projects like Hinkley Point C and Woolfer face severe delays, budget overspend, or cancellation here in the UK. Now, that's fission. That's a technology that has successfully generated energy for decades, and it's still difficult to get people to invest in it because you have these big upfront costs for building the plant, and you have a long-term fiscal commitment to disposing of the waste. And those problems really aren't going to go away for fusion, even if you have a wonderful fusion reactor that works. I mean, if it's ITER size, then those problems really aren't going to go away. Wind turbines and solar panels, by contrast, have substantial commercial advantages. I mean, take a look at the Kamuthi Solar Park in India. Now, that has a nameplate capacity that's greater than ITER. That's 650 megawatts of power it will produce, and it cost around $700 million to build. The construction stage only took 8 months, and it finished in 2016. Now, you can talk all you want about how the baseload power is not provided by solar and that solar is intermittent, but look at the advantages we're talking about here. I mean, this thing costs less than a 20th of the price of ITER. We know that it works. It actually generates power that goes onto the grid. And it was built in 8 months as opposed to the 20 years that it's going to take ITER to start working. So there really is no reason why, if you're an investor and you're looking to sell electricity as the end of the day, you wouldn't build one of these solar parks instead of investing in a crazy big nuclear fission or indeed fusion reactor. The energy generated by solar panels is already cheaper than the most optimistic estimates for the cost of electricity from nuclear fusion in these big ITER tokamaks. So, we're saying that ITER will be ready and generating electricity by 2050. Who knows how cheap solar electricity will be by then? Who knows how cheap the storage will be to make it effectively supply a baseload? So, in other words, unless it's extremely difficult and expensive to store the energy from renewable power sources, it's hard to see how tokamak behemoths will compete against renewables and storage in the cruel world of the free market. Now, it's true that many of the people who advance this kind of argument, they resent ITER for sucking up billions of dollars in government funding that might otherwise go towards their projects, leaving them reliant on convincing private investors. But this doesn't make concerns about ITER's commercial viability any less valid. Fusion startups are nothing new. In fact, if any of you bought a copy of Penthouse magazine in the 1970s, you were unwittingly funding one such project. The magazine's owner, Bob Guccione, as we talked about, poured millions of dollars into an experimental fusion reactor after reading an interview with a disgruntled fusion scientist in one of his magazines who felt that the mainstream efforts were doomed to failure. But as the race to find clean sources of energy to satisfy an ever-growing demand continues, and ITER continues at its glacial pace, dozens of companies with their own pet approaches have tried to beat them to the punch. If ITER-style tokamaks do turn out to be a commercial dead end, then these fusion dark horses might be the only way that the technology can be viable as a major source of energy. Various different projects use a fascinating mix of different technologies. Some are revivals of older ideas for nuclear fusion, others hope to leverage new materials or techniques to make fusion possible in smaller tokamaks. Why do the designers of tokamaks insist on building endlessly ever larger machines? I mean, it's not a totally ridiculous approach. For a start, intuitively, building a bigger reactor can allow you to produce more energy. If a plasma ever burns, i.e. fusion reactions supply the energy to keep the plasma hot, then its energy balance in that steady state is really important. It loses energy through its surface area, as particles leak and photons of radiation escape and carry energy away from the bulk of the plasma. It's heated by the fusion reactions, which are proportional to the amount of nuclei that can fuse, which is proportional to the volume of the plasma. So, it's losing energy out of the surface area, and it's gaining energy because of how much volume of plasma there is in there. So, typically, if you have a larger object, it will have a smaller surface area while enclosing a larger volume. So generally, a bigger device and larger tube of plasma means more reactions with a comparatively smaller surface area, and hence the amount of energy that you're losing is less. And so for this reason, pretty intuitively, bigger is often better for the fusion reactions. Then of course you get into the fact that getting the plasma into a fit state to fuse just requires large amounts of equipment. I mean, you need a big, complex apparatus to heat the plasma up to those temperatures, hotter, remember, than the heart of the sun, so you'll need to accelerate these neutral beams of ions to quick speeds. You'll need to produce these electromagnetic waves that resonate and heat the plasma. You need a big, powerful superconducting magnet, and all of the associated apparatus to cool that down to temperatures near to absolute zero, to contain the plasma. You need somewhere that you're going to store huge stores of energy to charge up those magnets. Remember when we talked about jet and its big set of flywheels? You need to make sure that all of this equipment is sufficiently protected from the damaging neutron radiation that arises when fusion takes place. And that shielding, to shield them from this neutron radiation, that's going to take up some space as well. So when you take all of this into account, it partially explains why the ITER apparatus as a whole ends up being a square mile complex in total. But then, of course, the bigger your machine and the bigger your device, it immediately hits you with all of the financial problems that we've discussed in Buzzkill episodes and just now. There are, however, trade-offs that arise in fusion engineering and design. So take, for example, the plasma pressure. This is defined as the density of plasma particles multiplied by the temperature. That fusion triple product, the one that we want to maximise to get a lot of energy, is then just the plasma pressure multiplied by the confinement time. You can get a larger plasma pressure if you have a greater plasma current, a stronger magnetic field, or a smaller plasma cross-sectional area. But there's an empirically defined limit as to how large that plasma pressure can be before you run into problems. It's called the Troyon limit, and the closer the plasma pressure gets to that limit, the more likely you are to experience disruptions in the plant. So when you're designing a plant, you have a choice. Do you design a small plant that operates with a huge plasma pressure and risk bumping up against the Troyon limit and damaging disruptions? Or do you design a slightly larger plant? This will have a smaller plasma pressure because the plasma will be less dense, but perhaps a longer confinement time, or it can produce more energy because there's more volume of plasma. But of course, if you design this larger plant, then maybe it's not economically viable. So it's really very, very difficult to understand precisely what configuration is going to be the most economically viable and the most feasible without disruptions. Because of course, disruptions have a cost in themselves. It means that your machine has downtime, it means you need more shielding to deal with them, etc., etc. The more heating you need to provide to drive up the plasma temperature, the more energy you'll need to provide to the system, and the more fusion reactions you'll need to earn that energy back. So you might think that one solution would be to have an incredibly dense but relatively cool plasma, really jamming in the plasma as much as possible and confining it with extremely strong magnetic fields. After all, typical plasma densities are around 10 to the 20 particles per cubic meter in a tokamak. That might sound like a lot. 10 to the 20 particles is 10 with 20 zeros after it, so it's a really large number of particles. But of course, it's actually much less dense than air, which has around 10 to the 25 molecules per meter cubed. So there's 10,000 times more molecules in air than there are in the plasma fuel in these tokamaks. So surely there's room for improvement here by having plasma that's at least as dense as air. Well, unfortunately there doesn't appear to be. The limit on number density, which is set by the size of the plasma cross-section and the current that's being run through it, is the least well understood. This limit, called the Greenwald limit, doesn't come from magnetohydrodynamic theory like some of the other limits that we've discussed. Instead, it just arises from empirical observations. Many experimental campaigns in tokamaks have shown that if your plasma gets too dense, if you try to inject too much fuel into the tokamak, then you end up causing disruptions and the magnetic fields can no longer hold your plasma. You might think that one solution then would be to drive a really high current through the plasma. After all, we've just said that if you have a high current in your plasma, you can have a more dense plasma amount. But there are limits to how large the current can be also. If the current driven through the plasma is too large, the external magnetic field struggles to contain the plasma as a whole, and the whole thing kinks and writhes out of control. There's another formula that determines the limit where this happens, the maximum current you can drive through the plasma before the kink instability kicks in. This turns out to be proportional to the external magnetic field, so stronger B fields can contain larger plasma currents, and inversely proportional to the size of the torus. A larger donut can contain a larger plasma current. So in summary, we have all these different plasma parameters we might try and control. We have the density, we have the temperature, we have the plasma current, we have the volume of your tokamak, we have the confinement time, we have the plasma current, we have the external magnetic fields, the shape of them, the size of them, the strength of them, etc. All of these different things that you can try to control, various combinations of parameters you can use, hoping to get better performance. And that's what a lot of these experimental campaigns really do. So although there are many different tweaks in all the different tokamak parameters that you can dream up that might impact on performance, there are issues because there are these instabilities that show up when you try and make any one parameter too large. But there are two clear roads to getting a better tokamak that come out of all of this. Either you build a larger one and you reap advantages from having more fusion reactions and a longer confinement time. Or, if you want to build a smaller tokamak, then you'll need to have high density plasma. If you want high density plasma, then to avoid the limit, you'll need to have a high plasma current. And if you want a high plasma current to prevent kink instability, you'll need a high magnetic field. So this is where we essentially end up. You can have big tokamaks like ITER, or you can have small ones with a stronger magnetic field that lets you have a bigger plasma current, a denser plasma, and therefore a smaller reactor. So most of the startups that are hoping to build smaller tokamaks are going to try to do so by leveraging stronger magnetic fields than those that ITER can use. Commonwealth Fusion Systems is one such startup and perhaps the most promising. Spun out of MIT's plasma physics department, they aim to leverage high-temperature superconductors that weren't available when ITER was first designed to create a much smaller tokamak. High-temperature superconductors like YbCO, yttrium barium copper oxide, are often capable of producing a higher magnetic flux density for smaller amounts of material, which may allow for a smaller tokamak overall. Theoretically, the amount of fusion power a tokamak of a given size can produce scales with the fourth power of its magnetic field density, so more powerful magnetic fields are very important. Its current design aims to produce a fifth of ITER's power output for brief 10-second bursts using a tokamak with around a quarter of the diameter of ITER. Yet these high-temperature superconductors pose more tricky engineering challenges than the niobium tin superconducting wire that's being used by ITER. This wire is far easier to create and manipulate at scale, but the high-temperature superconductors are ceramics rather than metals, so they can be brittle and temperamental, and no one has yet built large volume magnets out of this material. A further issue that's also plagued ITER and even Bob Guccione's Rigatron is the flux of high-energy neutrons. It's difficult to even test materials against this kind of radiation, because one of the only things that can produce neutrons of this energy are fusion reactions, so you sort of need a fusion reactor, or at least a fusor, to get it going. The smaller the tokamak, the more intense the neutron flux is going to be, because you're going to have a much smaller area with the same number of neutrons flowing out into it. Commonwealth Fusion Systems propose to use liquid shielding that can be easily replaced when it becomes irradiated, but, like all neutron shielding devices, this hasn't been tested yet, and it will result in some amount of radioactive waste from the tokamak. And of course, if the expensive and delicate high-temperature superconducting magnets cannot be properly shielded, then it's back to the drawing board. Commonwealth Fusion Systems has been financially backed to the tune of $65 million by oil company Eni and Breakthrough Energy Ventures, the venture capital firm whose list of investors reads like a who's who of tech billionaires. They argue that their proposed SPARC reactor, that is, the smallest possible affordable, robust, compact reactor, doesn't rely on any unproven plasma physics to work. Empirically derived scaling laws in plasma physics mean that similar behaviours can often be expected for smaller tokamaks operating at larger magnetic fields. While this reactor would still take hundreds of millions of dollars and years to build, its CEO, Bob Mumgard, hopes that the design could leapfrog ITER to produce net power more quickly than it can. Tokamak Energy are another private venture that hopes to leverage the decades of research expertise on the tokamaks to avoid straying too far from the scientific mainstream. The classic tokamak is a toroidal, that's a donut-shaped object, with a hole in the middle. Tokamak Energy uses a spherical tokamak, which basically just means that it has a much smaller central hole and a much smaller aspect ratio. When developing the theory of plasmas in tokamaks in the 1980s, researchers noticed that several instabilities, including the kink instability, were suppressed by changing the geometry of the plasma. So spherical tokamaks replaced the magnets on the inside with a single conductor, allowing them to be built more cheaply. Several spherical tokamaks were built alongside existing tokamaks, such as the massed spherical tokamak in the same Culham laboratory that houses ITER's predecessor, JET. They boasted improved resistance to instabilities, but the geometrical differences meant that the plasma pressures that could be achieved were lower, and the central conductor was directly exposed to radiation from hot neutrons. Many of the difficulties with making spherical tokamaks practical is that if you are actually substantially shrinking the size of that donut hole, you're going to be able to fit much less in that interior. Fitting in the vacuum vessel, neutron shielding, the central coil, and the coils that spread around the vessel for the tokamak in such a small space is going to prove difficult. And generally this means that you need to cut back on the neutron shielding, but this then means that you have some neutron exposure, which can damage the superconducting magnets and reduce their lifetimes. And of course, if you do have these hot neutrons flowing onto your superconducting magnet, they can also heat the superconductors above the temperature where they start becoming superconducting. Putting large amounts of cooling apparatus in the centre there will be difficult when you're already running out of room, so there are lots and lots of problems that can arise, which basically all arise from the fact that although you've improved plasma instabilities by changing the geometry, you now actually have less space to put all of your tokamak gear. We've already talked about, for example, the large mechanical forces that act on the coils in ITER. These are the magnetic forces that push these coils apart. And these have to be counteracted with big mechanical supports that keep the magnets in place. And of course, if you have a spherical tokamak where you don't have much space in the centre, you're again going to find it really difficult to keep those magnets in place. So ultimately, it remains unclear whether the advantages in plasma performance from a spherical tokamak will really overcome the disadvantages that arise from having much less space to cram all of these components in, which might limit the types of magnetic fields you can operate with or reduce the total strength of the field that you can actually provide. And it might also, ironically, require you to have an extremely large device, just so that the small internal donut hole is large enough to fit everything in. I mean, it's small compared to the device. If the device is huge, it can still be massive. That may then, of course, defeat the idea of having a smaller tokamak through having more stable plasma in the first place. And then, of course, you run into all the same economic problems that large devices like ITER might have. Although many in the research community were intrigued by the advantages of spherical tokamaks, they were a few generations behind the mainstream torus design, and their behaviour is consequently less well understood. Tokamak Energy, which spun out of Culham's research with the MASS device and is based in Oxfordshire, has received over £50 million in funding for its spherical tokamak, and in June 2018 achieved plasma temperatures of 15 million Kelvin. That's still not quite as high as JET's 200 million Kelvin, but it's getting up there. Much like Commonwealth fusion systems, they are hoping to exploit high-temperature superconducting magnets to achieve things that have defied previous generations of tokamak. So you can see that really it makes sense that there would be at least one company out there that's pursuing these spherical tokamaks, since in the 80s these researchers discovered that they had some interesting properties, they made plasma more stable, but they had some engineering trade-offs that you might have to consider. Ultimately, the mainstream community went with JET and ITER, and they said, we're not going to invest huge amounts of money in building a massive spherical tokamak, because we're not convinced. But it does make sense that someone else would be pursuing this little side avenue to see if it turns out that these spherical tokamaks are actually way better than the kind of thing that ITER is trying to build. Those who back tokamaks in general will point out that over the last few decades, their performance has increased by orders of magnitude. It might seem like the fact that nothing has so far succeeded in breaking even means that it's time for a brand new idea, but this failure to reach a symbolic, if important, goal does hide some considerable progress. Between the 1960s and the construction of JET, the fusion triple product of density, temperature and confinement time, that's the thing that really determines whether you're going to get energy out of your fusion reaction ultimately, that's increased at a rate comparable to Moore's law for transistors. It's doubling every few years, it's increasing exponentially. So who's to say that the next bright idea for a fusion reactor wouldn't also require decades of development and progress just to catch up with the tokamaks which have had so much investment put into them? But of the dozens of nuclear fusion startups out there, only a fraction are focused on tokamaks. While there are clear advantages to tweaking a design that is this well studied, it also means that many different tokamak devices have already failed to achieve break-even. And if it turns out that tokamaks really do need to be ITER-sized or substantially larger to be worthwhile building, then they might never compete financially with alternative sources of energy. So for that reason, many companies are still venturing into the unknown, in the hope that they'll find an easier, cheaper route to nuclear fusion. General Fusion, a Canadian company that has received over 150 million Canadian dollars in various funding rounds from the Canadian government and private investors, uses a technique called magnetized target fusion. This is a mix between confining plasma with magnets and compressing it rapidly to high densities and temperatures in an implosion, aiming to satisfy the Lawson criterion with contributions from confinement time, temperature, and density. Their reactor design is like something out of steampunk science fiction. Liquid metal, in the form of molten lead and lithium, is spun around rapidly, creating a vortex in the centre of the sphere. The plasma, held in magnetic fields, is then injected into the centre of this vortex. Then, steam pistons push the metal rapidly towards the centre. The vortex collapses and, hopefully, the deuterium-tritium fuel is compressed and heated to fusion conditions, and releases energy in the form of fast neutrons. This energy heats the liquid metal, and the heat can be extracted to drive a turbine in a conventional power plant. Founder Michael LaBerge, who described this as his midlife crisis plan to save the world from global warming in a TED Talk, argues that the liquid metal will also act as shielding, which will absorb the neutrons before they can damage any other parts of the reactor. Meanwhile, early prototypes of General Fusion's device, based on a concept that was first investigated by the US Navy in the 1970s, have created some neutrons, which is usually a sign that at least some fusion reactions are taking place. But producing neutrons is far from proof that you can produce energy. In Britain in 1958, the Zeta device, based on a technique called pinch, where a strong current is run through plasma and the resulting magnetic forces heat and compress the plasma, hopefully resulting in a burst of fusion, produced neutrons, as we talked about in our episode A Son of Our Own. The newspapers had a field day and reported that limitless energy was finally on the brink of being achieved, but as you remember, the neutrons arose from only a tiny fraction of nuclei, and Zeta had no hope of reaching break-even. It was famously an erroneous detection of neutrons that led Fleischmann and Pons to conclude that they had discovered cold fusion in one of the most embarrassing incidents in scientific history. When the US Navy originally investigated this idea in the 70s, they abandoned it for the same reason that laser fusion has fallen into the doldrums. It's extremely difficult to get the fuel capsule to implode exactly right, with the near-perfect symmetry that's required to allow inertial confinement fusion to produce more energy than you put in. Any slight deviations on the surface of the shockwave will cause Rayleigh-Taylor instabilities, with tendrils of plasma bursting outwards as the fuel is compressed, reducing the temperature, density, and hence the number of fusion reactions that can take place. LaBerge hopes that, now pistons can be controlled by servos and computers to be closer to simultaneous, operating within microseconds of each other, it will be possible to generate that perfect shockwave to achieve net energy gain and succeed where NIF's lasers have failed. While our current demonstration model uses 14 pistons, the final design is likely to require hundreds of pistons to achieve this all-important symmetry in the implosion and avoid those instabilities that the laser fusion has had so many problems with in the past. Now, skeptics would argue that if getting the spatial and temporal coherence required is difficult with lasers, in other words, if it's difficult to get all of the lasers to fire at precisely the same time, precisely at the correct locations, the beams of lasers can be very finely controlled using optical devices to within milliseconds, to within nanometers, to within nanoseconds. So trying to get this level of control mechanically with pistons might prove even harder if it's impossible with lasers. How can you do it with pistons? And I think I'd count myself as one of those skeptics. Meanwhile, surrounding the fusion target with a blanket of liquid metal is elegant in some ways. It would absorb the radiation and the heat and the neutrons, and potentially gets around all of the extremely complicated aspects of having neutron shielding and first wall materials. It provides a means for harnessing any energy you do generate from fusion, because that liquid metal can then have its heat extracted from it. You can mix lithium and lead, as they hope to do in their device, and absorption by the lithium breeds tritium, so that your reactor is producing its own fuel in the future. Remember we talked about how the tritium breeding schemes in tokamaks like ITER could be a big deal, because tritium doesn't naturally occur on Earth, even though it's part of fuel. But, while there seem to be lots of advantages to doing this, of course it has its own problems. You're physically compressing the plasma with liquid metals. You will struggle to prevent impurities from the liquid metal from getting into the plasma, and when that occurs, it's difficult to see how you'll get to fusion conditions, because the impurities will radiate away energy and ruin the idealized conditions for the fusion fuel pellet that you're trying to get to. In early tokamaks, remember, impurities were introduced simply by having slightly dusty tokamak walls, and they were enough to degrade and ruin the performance of these tokamaks just from dust on the walls. Impurities from a diverter or first wall that break up in ITER under pressures are a concern. And while you're essentially attempting to compress the plasma with huge amounts of impurity, it's hard to see how you don't end up with some impurities in your plasma target. There are some deeper concerns from some of the fundamental physics behind some of the ideas pursued by these startups. In short, many new fusion ideas involve some kind of non-equilibrium confinement system, i.e. the plasma is not confined for long enough for collisions and interactions to ensure that all of it, that means the ions and the electrons, reach the same temperature, or it's confined in such a way that avoids this equilibrium. Without going into too much detail, there's a paper from 1997 called Fundamental Limitations on Plasma Fusion Systems Not in Thermodynamic Equilibrium, which explores general properties of this kind of system. So why do we want to avoid thermodynamic equilibrium? The answer is that if we're in thermodynamic equilibrium, then the electrons have the same temperature as the ions, the nuclei that can fuse. But as we learned in the early stages of inertial confinement fusion, hot electrons can be disastrous for plasma. They radiate away large amounts of energy as they accelerate and decelerate. In fact, they radiate away so much energy that the energy losses due to radiation are likely to exceed any energy gains from fusion you can get. So you'll never have a self-sustaining burning fusion fuel. It will just end up cooling too quickly because of these electrons. The idea goes then that you might try to have the electrons being really cold while the ions are really hot. That way your fusion fuel, the ions, is fast enough to smash into itself and fuse together, while the electrons are nice and docile and they don't emit too much radiation because they're not going very quickly. The only problem is that essentially, if you want to keep the electrons at a different temperature to the ions, you need to transfer energy from the electrons to the ions. And what this paper showed was that generally, the amount of power you need to drive from the electrons to the ions is too great. In other words, keeping the electrons slow and the ions fast will also consume more energy than you can produce. So you need to have a system in thermodynamic equilibrium. You can't get around that, according to Ryder anyway, who wrote this paper. And Ryder also noted that this can make using different nuclear fuels rather than deuterium and tritium even more difficult, which we'll discuss next week. Nevertheless, though, there are plenty of attempts out there to generate fusion through shockwaves launched at hot, dense plasma confined by a magnetic field, magnetized target fusion, and they're being pursued at other institutions, including Los Alamos. Helion Energy, which has received millions from sources including the US Department of Energy and startup incubator Y Combinator, aims to generate this compression using pulsed magnetic fields. Their 5th generation device, VENTI, went online in 2018. So we'll talk about some of these ideas and some of the other startups pursuing different weird and wonderful routes that may, someday, hopefully lead to fusion, in the next part of this series next week. Thank you for listening to this episode of Physical Attraction. Remember, if you have any comments, questions or concerns, or you'd like to donate to the show, you can find all that information at our website, www.physicspodcast.com. We've got a PayPal, we've got a Patreon, we've got a comments box which goes to my email. I always read them and it's always great to hear from listeners, so send anything you like to that. You can also find us on Twitter at PhysicsPod, and the Facebook page is Physical Attraction. Until next week, then, take care.